Hey, good morning. Gonna make a start in a moment. How many people have we got? We've got about 10 at the moment. I just need to turn the audio off on this computer, although there's maybe some feedback. Right, guys, as usual, if you can just announce yourself as you come on. Who have we got? We've got Harry, good morning. Georgie, very good morning. Brett, shalom. Charlie, good morning. Nick, hi. And then we've got Hayden, good morning. Corey, you said Charlie. Charlie, you said Corey is also watching. Good morning, Corey. Ross, you're here. Great. Good morning. Ryan, good morning. Declan, good morning. Right. How many have you got? We've got 9 watching now. 7. Hey, numbers are going down. What's happening? Okay, everything seems to be okay on my end, I think. Good morning, Amy. Right, we're going to make a start, and it's not going to take too long, so I won't keep you too long. This afternoon is going to be a little bit longer, so I thought of maybe starting at 1:30, but I decided maybe 2 o'clock should be enough. It should just be an hour and a bit, and then we are through with it. And then there's one more tiny presentation to mop everything up, which is probably about half an hour. And then what I want to do is for 315 is just have a summary of all the criteria points, so that we can make sure we've addressed everything. And so it's going to be maybe three more sessions, and then it's assignment prep. Okay. I think I've got all your 309 stuff. I meant to go through it all, but I thought I better sort of try and finish off 315 with the presentations. I was working on those. Tomorrow, I don't know. You're probably were you told what you're doing tomorrow? Are you with Ian or with Vic or something, or with me? I don't know. Anyway, if you obviously there's a delay, there's this minute delay again, so just type it up and then we can look at that. So my plan for now is we're gonna do this little task. This afternoon is just one more session on measurements. On Monday afternoon is going to be a tiny session on sort of a mopping up session to get right to the last criteria. And then on Wednesday we'll have a couple of sessions. So that's probably by the end of the week, a couple of sessions for 315 with all the criteria we have missed out on, plus just a summary of everything. And then Friday next week, hopefully we can go through the assignment, or we do it on Monday, depending what you're doing on Friday. And then you'll get the assignment for this as well, the theoretical part. There's a practical element which you'll be free to do at work if you find opportunity to do so. So it would put the pressure off you. Or if you can't, then next time I see you at college, which who knows might be soon. I don't know, depending what's happening. Then we'll just focus on the practical bit for 315. Right. Okay, I'm just going through it. Tomorrow is catch up with stuff we've got outstanding. Okay, so I won't impeach on you. Infringe, not impeach, infringe on you tomorrow. Impose, that's it. Not infringe, impose. Impose on you tomorrow. So we'll do it on yeah, I don't know. I'll check out with I'm just reading what Brett is saying. Do we need to organize a session with you or Vic tomorrow, as it says on the timetable? I'll check out with Vic what's going on. So you may get an email in the morning, and then we can sort of move one session forward and go through that. The next session is not long. It's probably about half an hour or something, just to go through stuff, and then we've got a couple of longer sessions with a summary for the whole unit, excluding the stuff we've just done in the last couple of sessions. Okay, let's make a start with the task. Again, please, when you do your write-up, it's very important that you upload everything to one file as evidence. I I'm aware that there's some problems with one file, and I think some of you have been in touch with Gary, which is great. But anyway, whatever you have, if it's electronically down, just let it go into the abyss of your USB stick. But that you've got everything available, so when one file is up and running for you and everything works fine for you, that you can just upload everything to one file. We'll get it sorted. Yeah. I'm probably in the same boat as what you are, so I'm going through it and trying to mark on one file, and so it's like some of you can't see what I've marked and so on. So some problems still there, some teething problems. Okay, Amy, could I have some help with 308? Yeah, Luke as well. I don't know, you're here, Luke. Great. You've been asking as well to give you some feedback on 308. Maybe we could do a 308 day tomorrow. I'll just be available for 308, or if there are questions you've all got problems with, we can have a YouTube session as well. So it's up to you. So let's leave it open. Yeah. So I'll be here tomorrow morning. I'm all yours. So whatever you want me to do, I'll be doing it, and then we carry on with 315 on Monday afternoon. Yeah. Okay, Brad. Okay. Okay. Like I said, with Brett, you will carry on with your 308 assignment. I'll be available for you. So if there's something you're all worried about, as far as 308 is concerned, just let me know, and we can then have a YouTube session. If not, if it's just like individual concerns with parts of your assignment, I know some of you have. I think some of you have finished, some of you have gone quite a way, and I'll just be available. So via email, contact you via email. Okay, right. Let's go to the task. We've got task number 1. A wavelet engineer is asked to change a 3-phase motor on a production line. As it is about lunch and everything stops for 1 hour, he decides to change the motor over the lunch break. Yeah. Since time is of the essence, and everything needs to be done within the hour, he decides not to do a log off takeoff, and not to bother with the permit to work. What could happen in a worst case scenario? Okay. This is, by the way, quite real. When I was working in industry, we were doing shortcuts all the time, and the essence was that very often, you didn't have time, you were under pressure, you had to do like 3-4 things at the same time, and a machine was just not in use. Yeah? So if you had to do some work on it, you just did it there and then. Yeah? You didn't ask any questions, you just did it. Yeah? And then it was interesting as well when you worked with big companies like British Steel or Tinsley Wire was one of them. Everything had to be done by the book with the big ones. So you had like guys who were employed, they were just health and safety guys. They were employed and they were checking everything. So if you didn't work by the book, you were in trouble. You were in trouble straight away. And we were told as well and said, look, whatever these guys say, you do it. It's no question, no nothing. Okay, bullet points. It's over to you. I know there's this minute delay. Give me some bullet points. What could happen in this scenario? Just little statements. And very good morning to you, Sam. And good morning to you, Joe, as well. Let me just write it here in the text box. Okay. Yeah, okay, that's a biggie. Thanks for that, Georgie. Someone could come back and start a machine not knowing work was being carried out. Fatalities, yeah, you're right, that's a biggie. What else? Just a bit more on this. Hayden, the factory starts up early and somebody turns on the machine because they don't know he's working on it. Yeah, spot on. Big problem. Yeah, and again, that's partly the reason why there are permits to work. So when you, for this one, I'm just trying to think. Have we got? You have to make points in the assignment, so you can make this point. That's the reason for permits to work. Yeah, so that nothing gets accidentally turned on or is put back into operation. Ryan, serious injury. Yeah, spot on. I mean, he could kill himself or the people he's working with, and others could suffer as well as a result of it. Yeah, you don't know how the production line impacts bits further down the line. Yeah, he will be handling. Does it say he's been changed as three-phase motor? Three-phase motor. Yeah. So it's electrical equipment. Okay, what could happen if it's electrical equipment? So obviously he has gone and switched it off, but he didn't do a tag off and a log off. Okay, good point, Hayden. I'm just going to read it out. Not worst case scenario, but because he's done it without telling anyone, then somebody could do the work again and waste time and parts. Yeah, spot on. Yeah, and again, this is. Charlie, get disciplined as a result of not following legal requirements. Spot on. Yeah. So that could be instant dismissal. Yeah, for not following and abiding by rules. There's a story. A friend of mine, something similar went on. He gave him instructions. He was the foreman in a woodworking factory or workshop, and he gave somebody the rules of what to do and how to operate a certain machine. The person thought he knew better, and he lost his hand as a result of it. Yeah. So it's fortunately, I mean, my friend, he was very finicky about the whole stuff, so I made him sign because he knew how dangerous this machine was, that he would only operate in a certain manner. Yeah. And because he had a written evidence that he had done this, there was no comeback on him. Good morning, Alex. Okay, few more points. Callum, what do you think? What else have we got? Callum, Sam, what do you think? Nick, Declan, give us some points or give us some beef. Right. As I said before, I mean, this is real stuff. This is when I look back, sort of the way we worked in the 80s. This was actually quite common. Sort of health and safety. The legislation was there, but people considered it more like it's nice and it's a best effort thing, but it's a little bit unrealistic and it's just too much hassle to follow it all. That was sort of the attitude you had in the late 80s towards all this, and it all changed in the 90s, and obviously this is now. It makes me feel really old, when you talk about this stuff. We are now how much 30 years down the line from that, and moved on quite a bit. And I have to say, when you look at work conditions today, I think the number of accidents and the dangers at work are a lot less than what they used to be. Okay, Nick. Instant dismissal, death, injury to other, not following legal requirements, company policies, requirements. Yeah, spot on. Okay. Right, I'm going to move on to the next task. I think we've exhausted quite a bit of here. Again, I'm aware there's a minute delay, so if some of you come in. Declan, you come in. There's not much more that I can add. Yeah, very dangerous and safe. Yeah, it's fine, Declan. That's I agree with that. I think we've said everything. Right. Let's move on to the next one. And my keyboard is not working. Try again. And it will work. Three-phase motor suspected to be faulty. Determine the equipment you would use to test the three-phase motor to determine a possible fault. Yeah. 2 times determine, should have used a different word. But anyway, we've got a 43-phase motor. How can you test it? What can you do to try and find out what's going wrong with it for your diagnostics? And that's sort of going back to the instruments we were looking at right now. Okay, just a couple of bullet points or statements or whatever. There are about 3, 4, 5 different answers possibly. A couple of tests you can do on the three-phase motor to try and find out what's gone wrong. Okay, down to you now. Okay, insulation continuity tester. What would you test and how would you test it, Nick? Somebody else feel free to jump in and answer. How would you do an insulation test? How would you do a continuity test? You look at energy consumption. Yeah, it's good point. So that would be like a power meter or something. Okay, it's one thing. So if it suddenly goes sky high or goes down, could be the other way as well, so that the motor just doesn't have any power anymore. It's what you do. Okay, continuity test. Charlie, how would you do the continuity test? Mega tester, okay, so insulation test. Again, how would you do it? What would you test again? So where would you put the lead for the mega tester? Rhine, insulation resistance between each phase. Okay, yeah, that on the coils, I would imagine, on the windings. So you would have 1,000 volts. Yeah, that's spot on for the insulation test, and 20 ohms for the continuity test. And a vibration analysis. We didn't cover this in the presentation, but that's a biggie now. It's very popular now. Sort of a lot of companies realize that reducing vibration of a motor will actually extend its lifespan significantly. So there's a lot of this stuff going on for vibration testing and reducing the vibration. Test continuity over each winding, yeah, spot on. Spot on. Nick, cease bearing, yeah. Again, could be a thing. How would you test for cease bearing though? What would you do? How would you do this? Okay, then we've got the insulation test by Nick, 20 ohms onto each of the windings down to earth. Yeah, that's spot on. Yeah. So if it depends, the way you have to imagine is you've got the wire, the enamel wire, which is wound up. So it's got this enamel insulation around it. It's wound up on a former, and if the thing goes too hot and some of the enamel is leaky and the insulation is breaking down, it could go against the body of the motor, and or it could be somewhere inside the windings as well, so that some windings are shorted out. So effectively the coil has got a shorter path, so it becomes a smaller induction that's generated. So it might still work a little bit, but not quite as efficient. Just between W1 and W2. Okay, yeah, spot on. Then you've got U, V, and W. That's right. Okay. Okay, good. A few more tests which we can do. I'm sort of still missing some. So we talked about, especially with the presentation in mind, so far we talked about continuity test, yeah, sort of measuring resistance, and then we've got the insulation test, and then we measure the power consumption. What other tests could we do? Here we go. Brett's got it. Thermal imaging, thermography. Just take one of these temperature gauges, hold it on the motor, and see where the hotspots are. And sometimes that can be a giveaway of something having gone down. So if a coil is shorted out somehow, what you'll find is there's more current going through potentially, and it'll heat up a lot more, generate a lot more heat, and that might be an indicator that there's something amiss or something is wrong. Oil analysis, good point. It's not part of the presentation, but yeah, it's a good point. Oil analysis. Especially for big motors, where you've got gearboxes and the bearings, which may be suspended in oil. There are companies. A friend of mine works for one of those companies, is Bombardier, and they are just doing this all the time. It's not that expensive either. It's like I think it's about £8 for an analysis, and you send your oil and a sample in, and they just check it out and tell you, how much bits of metal are in there in the oil, suspended in the oil, and then you've got a rough idea of the status of your bearings, or whether your bearings are on the way out. Right. Did we cover everything? Yeah, thermal imaging, that's the one I was looking for, Brett. Thanks for that. Okay, let's move on to the next slide. Task 3. A circuit on a production line is showing a fault tripping the RCD. What test equipment would you use to be able to diagnose the root of the problem? So what tests are you looking for this one? Someone give it a go. So the RCD is stripped. What do you want to find out? So earth fault current. So it's a DMM, but there are also specialist meters for earth fault current. Don't know whether it's this presentation or the next one when we're going to go through that. So you have the specialist equipment for that as well. What they're looking for is this. They look for the earth resistance, the fault path, but they also look for earth fault currents, whether there are any or they're going on to this. But yeah, that's the one. That's what we will be looking for, to just check the system, make sure everything is okay, and make sure there's no leakages occurring as well. There are no faulty currents going down to earth. Thanks for that, Nick. Thermal overload as well. So the RCD stripping could be a thermal overload thing, which would cause the system to trip. Yeah, that's a good point. Okay, we're going to look at this equipment. I think it's the next presentation. We're going to look at this on this afternoon, not tomorrow, this afternoon. So that's the next presentation, which is just about instruments and how to use them. So we're going to look at that as well. There's a couple of pictures of what they look like. I have to admit I've never used them. I've never seen them used either. So I think normally when this happens, you just... I was obviously using a DMM to find out what's going on, and that was enough. And then you've got your mega... the insulation tester for the other side of things, but if the insulation is going down in certain areas. But I have to admit I've heard about them, I've read up about them, but I've never used them. The earth loop impedance test equipment. Are you using them? Question: have you ever come across them in your apprentice life at Hovis, Coca-Cola, and Princes, or what's the situation? Have you come across them? Sort of earth loop impedance test equipment or earth fault current test equipment. Gonna have to wait for a bit to come through. Any responses? Anybody used them as yet, or you haven't? Or you can say no. It's not important. Just sort of interest. Just want to see whether they are in use. Yeah. Okay. That's a multimeter or ammeter. Yeah, it sounds like what we were using as well. So it's quite expensive equipment as well. Yeah, it's pretty much straight on. So you check out whether the machine is faulty or the RCD is faulty. An RCD is cheap. You just change the RCD. If it works, it was the RCD. If it's still tripping a fault, then it's a machine. That's pretty much the easiest way to diagnose a fault. Ryan, used to test newly fitted RCD and socket outlet before. Okay, interesting. Thanks for that, Ryan, for the feedback. I used to work when I was going all over Yorkshire on different sites and steelworks and so on. I was working for a small contractor, and they were just specializing in certain installations, and that was my job. So I was just going around and checking out things, but again, this contractor, everything is done sort of on the cheap. Whereas sometimes when you work for the companies, the equipment you get, like British Steel and Tinsley Wire at the time was quite big, and obviously the equipment they had was much more sophisticated. And okay, Brad, use a DMM to test to see if a motor is pulling too much amps. Okay, on load checks maybe. Okay, yeah, okay. So again, we're going to look at the DMMs as well. There are two types of meters. There's one which just picks up the magnetic field, and the other one where you actually have to have the current going through. Within an electrical concept or context, you would use those clamp-on meters, and obviously the other meters just wouldn't work. It's just more for electronics engineering, for the tiny finicky stuff where you're looking at milliamps or maybe an amp. But when you look at industrial applications, you're looking at huge amount of currents, and if you used a DMM, you would have to break into the circuit and take the measurement from one side to the other, and it could be very dangerous and impractical as well. So you've got these clamp-on ammeters, current meters, which is a lot easier to use and to see what's going on. Okay, let's move on to the next task, which is quick questions. Why would you want to use an analog meter over and above a digital meter? What voltage would you choose to use for an insulation test on a three-phase system? What is the lowest acceptable voltage for an insulation test on a single-phase system? Name two disadvantages for using analog meters. What could happen if you use a digital meter in an environment with a lot of static electricity? Okay, let's give it a go. Please, all of you, just answer a couple of questions so I can see everybody is still on the system. Sam, I haven't heard anything from you so far other than good morning. Give us a go, give us an answer to a couple of those questions. Who else has been quiet? Let's have a look. Okay, so Sam, Harry, Luke. Who else have we got? Who's been quiet today? Um, Callum as well. Give us some answers. Okay. Okay, that's for the voltage for insulation is on a three-phase system. What voltage would you use so to do the test? So 415 is on a three-phase system, Sam. What voltage would you use? Ross, okay, instant readings. Yeah, for an analog meter, that's an advantage. Last one, false readings. What can we do? Yeah, spot on, Sam. Yeah, okay, Ryan, thanks for that. Good point. Analog meter disadvantage is that people could interpret the reading differently. To do with the scales, sometimes you've got like a 10 scale, a 25 scale, and if you go for a maximum reading of 100 volts and you're on the 10 scale, it just shows you 5, but really it means 50. Okay, Hayden, I have to put an analog in the circuit. It may skew results because, yeah, spot on. Yeah, if you put if you measure a voltage into an analog circuit, then you introduce a small resistance, not small, but it's sort of in the order of about 100k, a couple of hundred kilo ohms, into the circuit, and this might skew up the readings. Yeah, so if the resistor you measure, or the resistance you measure the voltage across, is similar to the one you are introducing, then the value would halve. You would just read half the voltage. Okay. Let's have a look. Disadvantages you interpret the meter. Okay, Declan. An analog meter is not as accurate as a digital meter. That's, yeah. Again, I mean, some of the old guys, they would probably have a big argument with you, Declan. They would say, yeah, no, they are better than digital meters. They are much more accurate and so on. But again, you've got the reading problem, and it's right. You know, with a digital meter, you get a spot-on value. There's no umming and ahhing. Some of the cheaper ones are not that accurate. Some of the more expensive ones, they tend to be spot on. Same, by the way, same with the analog meters. If you get an AVO meter, they are renowned to be fairly accurate. Yeah? So all the components are high-grade components. But the problem is, if you look at the scale from an angle, you get a slightly skewed reading. Yeah? So you need to be looking at the needle from right on top of it to get the right reading. But good point. Yeah, I tend to agree with you, Declan. Okay, but disadvantage is you have to interpret the meter. Yeah, that's a big disadvantage. Some 500 volts. Yeah, for which question? For the three-phase system or for the single-phase system? That's my question to you. Where do you want to do a 500 volt insulation test? Aiden, you have to put analog in the circuit and it may skew results because of this. Okay, spot on. Yeah. Talked about this. It's heavy, yeah, the analog one. It's true, yeah. Some of them actually not that heavy. The AVO is really heavy. I mean, it's not something you put in your pocket. It weighs an awful lot. I think I have to get one. Yeah, just for the sake of getting one. But I always sort of stayed away from that. But they're historic. Yeah. Callum, an analog meter's magnetic field can be damaged by dropping it. Yeah, it's got a full-scale deflection meter. It's called an FSD, and it's based on a little coil. Some magnetism is generated, and it interacts with a permanent magnet, and so you get a reading, yeah, and a little spring, and if you drop it, it actually can damage it. That's spot on. Thanks, Callum, for that. Brad, could damage the meter if it's wired up the wrong on the probes. Yeah, spot on. So if you don't get the polarity right, you can damage the meter. Callum, it'll make it less accurate when you drop it. Yeah, that's spot on. Thanks for that, Callum. If it's wired up wrong, yeah, can be a problem. Ryan, wrong setting could destroy the AMM. That's right. Hayden, do you think it's worth having both digital and analog today? Personally, I would say yes. Yeah. One advantage for analog I haven't seen yet. You haven't mentioned it yet, or I've not picked up on it. But there is one reason why I would always keep an analog meter around. Probably wouldn't use it very often, but I would keep it around. Pegging an AM. I don't know. Did I put it in the presentation? Um, Must be a spelling error or something. Priority is right term. Okay. I'm just looking through the making less accurate. Did I miss something here about pegging? Polarity. Okay. Anyway, right. Just to move on to the next slide, and then we are almost done today. One good reason for, in my opinion, for an analog meter is if you look for intermittent faults. Okay. Just reading this is something. If I want to go. Okay, good. Don't know the terminology. It's probably knocking it. If you knock an analog meter, that can be a problem. If you knock it, not sure about the term. No idea. No idea. Analog doesn't need a battery, and you're right, Hayden. Analog doesn't need a battery if you measure voltage or current, yeah, because it's just using the full scale deflection meter and a bunch of resistors. And when you switch those the control knob around, you're just selecting between different resistors, which then control the current to the full scale deflection meter, and you get a reading. So you don't need a battery for an analog meter to make it work. Actually, it's quite an advantage. The only time you need a battery for is when you do resistance measurements. For that, you need a battery. For voltage and current measurements, you don't need one. What else? The main thing I would keep an analog meter around is to look for intermittent faults, and is when you've got intermittent faults. So if you've got, like, for example, a sudden voltage drop or something, and you want to see whether this is taking place, and maybe today, if you've like a PLC or something, and you've got a power supply that's cutting out every now and then, it might cause a PLC to reset or a sensor to reset, and then you would have obviously problems along the line. You get like fault signals, and stuff will turn off or turn on or whatever. It's very hard to find this with a digital meter. If you've got an analog meter, you just look for the needle, and if the needle starts jumping about a bit, you can see straight away that something is wrong and something is amiss. So that's the reason I would use an analog meter, and I've used them in the past. What you find with digital meters is not as much an issue today as what it used to be in years gone by. They have a sampling rate, and they need to sample the data. So they take they look at the data, they get an average reading, and they then just display it on the screen. But it takes some time for those numbers to be generated. So it might be half a second or a quarter of a second. But sometimes when you get an intermittent fault, it doesn't pick up on it. So the numbers, they don't start going up and down. And if they start going up and down, it's very difficult to see what's going on because of the time it takes to sample it. Some of the modern meters, they operate a lot faster, almost in real time. And some of them have even got like an analog display, like a little bar which goes up and down, to let you see that something is going on there. So, for example, that the signal is going up and down. So this, even on a digital meter, you've got something like a de facto analog display at times. and they are a lot faster. But the problem as well is if the numbers jump up and down, it's hard to see what's going on. With an analog meter, you see it straight away when there's a problem. And that's sort of my take on why it's still good to have an analog meter, at least to have access to one. Yeah. Not necessarily to use it as your main meter, but to have access to one. Okay, moving on. So questions 2. What happens to a live circuit when you take a measurement with a digital multimeter? So do you impact the circuit in any way? The next question is, you measure an earth resistance of 500 milliohms, a fault occurs at a current of 100, and a current of 100 amperes generated. What is the voltage dropped across a conductor? So it's just a little bit of Ohm's law. And could this voltage be considered lethal? Okay. Let's give it a go. See what you can come up with. First one. What happens to a live circuit when you take a measurement with a digital multimeter? I think this is the last slide. We're almost done, and then I can let you go. Right, okay. We got a calculation, so let's see whether this is right. So what is the formula for V? Quickly. What is the formula for V? V is equal to what? Okay, Sam. Yeah, I agree with you. If it is 200 volts and it goes across the heart and it's AC, it's potentially lethal. Okay, let's have a look again at the calculation. What is the formula for voltage? Somebody, please. I times R. Okay, so 100 times 0.5 is what? Thanks, Amy. Spot on. Yeah. So, what is the voltage? Hayden, thank you for trying and being the first to come up. But what is it? What is the voltage? The actual voltage we're looking at? $50. Okay, spot on. That is considered, I don't know whether you ever heard of something called SELV. It's SELV. Let me just type it in. SELV. Yeah. And this refers to safety extra low voltage. And okay, safety extra low voltage. And it's normally voltages, as far as AC is concerned, below 50 volts or up to 50 volts. Yeah. And it's considered to be safe. Yeah. So I would say you can feel, if you get a shock of 50 volts, you can probably feel it, depending on your physical condition. But it's unlikely to harm you. And unless you've got a very weak heart, it's unlikely to kill you either. This is normally considered to be safe, yeah, to be safe. Again, but it gives you an idea. So if you've got a half an ohm resistance on a conductor, which is quite realistic. You sometimes get more, sometimes a bit less. But when you get something like a huge current, for example, if you get about 200 amps or something, you're already at, with zero point 0.5, you're already at about 100 volts, and then it gets a little bit more critical. Okay, but Nick, what you have to bear in mind is you need a voltage. Your body has got a very high resistance, so it goes up to, depending what your body is like, but it could easily be about 100,000 ohms. So you need the voltage to get the current through your body. So the 100 ampere is not going through your body; it's going through the conductor. But it generates a voltage across this conductor, which could be going up to 50 volts. No, not at 50 volts. I doubt it. Whether you would get a bad burn or something. You need a higher voltage for that to get a burn, to fry your skin. Okay, I don't know whether I did this with you as a class, but normally what I tend to do is when I talk, I normally do it for 308. I take meter readings of your body resistance, and I'm sure I've done it. I don't know whether you remember, but meter readings of your body resistance. And if I haven't done it, please try it out. Don't take an insulation meter, don't take a mega, just take a normal meter. And what you find is that the readings are really, really high, really high. And also, if you happen to take a mega, and again, make sure you don't do it across your heart, you just do it across, your forearm or whatever. What you'll find is with an insulation test that the resistance actually goes quite down quite a bit. So whatever values you get, so for example, if you get typical values about 100,000 ohms, from one end to the other hand, it's about 100,000 ohms. As soon as you apply a higher voltage, you get it's called a lower contact resistance. The contact resistance goes down, and as the current goes through your skin, and the total resistance will go down from 100,000 K to, I don't know, maybe 50 or 10 K or something. And so you can then get quite critical voltages or critical current through your body, which will stop your heart. The figures which can stop your heart, the figure I've got in my mind is about 25 milliamps, which is the stuff you use to drive an LED. So if that current goes through your heart, it can potentially stop it. Okay, got a few more comments here. When you touch 24 volts, you get a bit of a tingle. Yeah, that's right. I go along with that. 50 volts, you get a bit more of a tingle. 120 volt, 110 volts. I was working on some systems in Canada. A friend of mine got a farm there. So I was working on some feeders, and some of the wiring was really dodgy. The insulation had gone, and it started raining, and I got a shock. And normally 110 volts is supposed to be safe, or safe-ish. But it was very painful. It was very painful. Okay, the current is limited on an insulation tester. It's just a very, very low current. It's almost, I wouldn't say it's like static, but it's it won't allow for a huge current to go through your body. That's really the thing. And then the other thing, an insulation tester is DC. It's not AC. If it were AC, it could cause a lot of problems to your heart if it went to go through your heart, even if it's just a low current. But it's DC, so it doesn't tend to be quite as lethal. I understand in operating theaters, when they do heart operations, they use AC to stop the heart. When they put people on an artificial heart-lung machine to operate on the heart, they use AC to stop the heart, and they use DC to start it back up again. So the fibrillators, they are pumping out DC. Yeah, a welder tends to be ideally should be DC as well. Yeah. And the voltages go up quite a lot, so they go up to 40-50 volts. But with a welder, it's all about current. They try to generate a certain amount of current for MIG welding and TIG welding to melt the wires. Yeah, and 110 volts, you can feel it. You can feel it. The systems we've got here in the UK, we've got the yellow box, for hand tools. So when you've got a drill and you work with it outside. And what they've done is they've on the secondary winding, so they've got an isolating transformer there. So it goes 2 to 1, goes from 240 to 120 or 110, and then the center of the secondary winding is earthed. And so the whole idea is if you get a shock, the maximum shock you should get from the 110 volt system is about 55 volts. So that's again almost in the self region where it's supposed to be or considered to be safe. Yeah. So that is the system. So these are the yellow boxes, and you may have seen them around in the factory when people have got hand tools and then plug it into a 240 volt supply, get a little yellow box with a transformer, and then on the other side you've got the 110 volt equipment. Okay, first one, what happens to a live circuit when you take a measurement with a digital multimeter? What happens? What impact has a digital multimeter got on the circuit? That's pretty much what I'm asking. Somebody, just give me the answer. And I think we are done after this. That's the last question. Okay, good answer. Good question. Could it trip the circuit? It could, but I doubt it. It depends how sensitive the trip switch is. I doubt it. The answer I was looking for is actually nothing. Do you know why nothing is happening? Or most likely nothing is happening when you go on a live circuit with a DMM. What is the reason for that? Yeah, as well, Brett. I mean, obviously, the only time you get a signal from the multimeter into the circuit, and you shouldn't do this on a live circuit, if you do a resistance measurement. Never do a resistance measurement on a live circuit. I mean, first of all, you put some signals in there, so depending what it is, it could cause problems. The voltage on a DMM is fairly low. It's like a volt or 2 volts or something. It's not that much in it. If you've got an analog meter, it tends to be about 9 volts. It's a bit more. But for a DMM, it's very, very low. But then because there are already voltages present in the circuit, so the reading you get is just totally irrelevant. So for a resistance measurement on a live circuit doesn't make sense. But obviously, if you want to measure voltage and ampere, you need to be on a live circuit. Otherwise, you can't get a voltage reading. So the answer Hayden gave is correct. Yeah, nothing happens. But why? Why is there most likely nothing happening? What Amy is saying, could it trip the circuit? It really depends how sensitive it is. It shouldn't, but it potentially could. With an analog meter, it's much more likely that it would trip the circuit because you introduce a relatively low resistance to the circuit, whatever you're measuring when you take your voltage measurement. And with relatively low, I mean it's still about 100K or something. But what about a DMM? Okay, let's see whether I get an answer. Be brave. It's the last answer, and then I think we are done not for today, but for this morning. Somebody, just be daring. Why is most likely very little going to happen, or virtually nothing? I almost gave you the answer. So wait for a moment. Okay, what happens to life circuit when you take a measurement with a digital multimeter? Hayden said mentioned the correct answer. Nothing is going to happen. But why? Why is nothing going to happen? What is good about a digital multimeter, which is less so with an analog multimeter? Okay, yeah, it's battery powered. It's not. Yes and no. Yes, obviously it needs to power up the circuit to get the reading and everything. Um, okay, somebody else. Just give it a go. Uh, the answer is correct. Yeah, but I'm looking for another point as well. So again, the problem with the analog meter is it introduces a low resistance. What is good about a digital meter? Just take it from there. Yeah, okay. When you measure a voltage or current, there's no voltage which is applied to the circuit at all. It's not. Um, yeah, okay. If Amy comes up with low current, the meter will take a very very low current from the circuit, a really really tiny current. But why does it take only a tiny current? So we are looking in the order of nanoamps. Yeah, really really tiny. But why? What is the biggie about multimeter that's not so good? That's it, Ryan. Spot on. Thank you. It's got a high internal resistance. So the internal resistance for all DMMs is about 2 million ohms. Yeah. I try to measure some of the modern ones, the internal resistance. You can do this if you've got like two DMMs. Use one DMM to measure the resistance of the other DMM. So if you put like a voltage measurement, and then on one DMM you get the voltage reading for the resistance measurement of the other one, and the other one gives you the resistance now of the other DMM. And what I found is they go up to about 5 million ohms, sometimes even above 5 million ohms. Yeah. And yeah, Declan, that's correct. That is called impedance. Yeah. Impedance is a mixture of reactance and resistance. We're gonna look at this. Are we gonna look at this again in one of the units? But anyway, that's just a mixture of the two of them. Reactance is when actually we're gonna look at this in the next session. So let me just anticipate a little bit. So reactance is when there's an apparent resistance which responds to frequency. So if you've got an alternating signal like an AC waveform, and you've got a reactance will respond to that. For a coil, the higher the frequency, the higher the reactance. Yeah? So it's like a resistance which doesn't seem to be there in the circuit in DC conditions, but it appears as soon as you apply frequency. So that means AC. And when you look at capacitors, in DC conditions, a capacitor is like a piece of rubber, so nothing is going to go through it. If you apply AC, the higher the frequency, the lower the reactance or the apparent resistance in a capacitor. And then obviously you've still got your DC resistance, which stays the same in AC and DC conditions. Your normal box standard resistance. And that's called impedance. Taking both of them together is called impedance. And that's right. It's got a really high input impedance, and so when you apply it to a circuit, there's virtually no current taken out of it due to this high resistance. And we are looking in the realm of nanoamps and stuff like that. And one problem is, I think, did we mention this? Let me just go. Yeah. One problem is obviously because there's so little current taken out of it. If there's a lot of electrostatic noise around, sometimes the noise can be picked up by the leads of the meter, and you get a reading for the electrostatic noise as well. On account of this high input resistance or impedance, and it not taking out any current from the system. Okay, and that's it really. Guys, thank you for tuning in and for watching. 19 people at the moment, so thanks a lot. I really appreciate. The next session is going to be at 2 o'clock. It's going to take about a little bit more than an hour. So it's just picking up the criteria points. I think it's 2.3 or 2.4 and whatever is left. And then there are sort of a couple of things which we haven't covered. We're going to mop this up on Monday afternoon. And then we've got the summary for the stuff we've covered in the past. Just like a brief summary of everything. And then, filling in any holes which may be there as far as the criteria points are concerned. Okay, what does it mean by impedance? Okay, let me just go through this one more time and see whether I can I do this. Impedance is called Z. Let's have a look. I'm going to type it up and then maybe it's easier. Impedance symbol. And then we leave it at that. Reactance is okay, so reactance is changing resistance with frequency. So frequency is AC, 50 hertz, so it changes 50 times. But you could have like other signals as well. Like in America, you've got 60 hertz, or you could have high frequency stuff. Again, we're going to look at this later on. Resistance, okay, and reactance. The symbol is X. And so you've got XC and XL. So one is capacitive reactance, the other one is inductive reactance. So they're both slightly different. Again, we're going to cover this maybe later. And Z, right, the formula for Z is, there we go. I just gonna say, so Z squared is equal to R squared plus X squared square root taken out of this. No, sorry, let me correct this. So Z is equal to R squared plus X squared and the square root taken out of both. So that's equal to Z. That's the formula for impedance. And X normally is XL minus XC, and that's sort of the result which comes out of it. So in brackets squared. So that's a formula. You don't need to worry about this at this point. It's just a mixture of both of them taken together. So you take the resistive element and you take the reactive element. You add them both together, and when you've got inductive and capacitive reactance, they both subtract from one another. So normally XL gives you positive lead, XL a negative lead, and then in the phase shift, and you add them both together, or subtract one from the other. Then you add the square value of the DC resistance and your reactance, and you take the square out of this, and that is the square root out of it, and that is that. Okay, that's all you need to know for now. We're going to pick it up in the next session. What's the time? We've done about an hour, a little bit more than an hour. I'll see you this afternoon at 2 o'clock. I'll send you the link sort of lunchtime-ish around, so I'll set it up and send you the link, and we will have the last sort of criteria points picked up on this unit. And okay, that's it. Thanks for coming on this morning, and I'll see you this afternoon.